In this presentation, I will discuss the utility of using X-ray CT to non-destructively observe the status of joints between dissimilar materials. This is the outline of my presentation. First, I will provide a broad overview using X-ray fluoroscopy or X-ray computer tomography to observe materials. Then I will present two examples of using X-ray CT to observe samples of joints between dissimilar metals. First, I will describe some characteristics of X-rays. X-rays are a type of electromagnetic wave, like radio waves, infrared rays, visible light rays, and ultraviolet rays, but they have a shorter wavelength that allows them to pass through objects. However, the amount of X-rays that can pass through an object depends on the thickness, density, and atomic number of the atoms in the object. X-ray fluoroscopy and X-ray computer tomography are techniques that use those X-ray characteristics to observe structures inside objects. Next, I will explain the operating principle of X-ray fluoroscopy and X-ray CT. This illustration shows the operating principle of an X-ray CT inspection system used in industry. The object to be observed is placed between the X-ray generator and X-ray detector. Then X-ray transmission data is obtained by creating an image based on the variations in the amount of X-rays transmitted through the object depending on the material characteristics, such as thickness and density of the object. Fluoroscopic images are obtained by creating images from data acquired from transmission through the object in one direction. In contrast, for CT imaging, the object is rotated 360 degrees while being irradiated with X-rays to acquire a collection of X-ray transmission data from a variety of directions. Then that transmission data is reconstructed into images to obtain several hundred or more cross-sectional images. Then the cross-sectional images can be combined to also create three-dimensional images using special image processing software. It may be difficult to understand the differences between fluoroscopy and CT from the previous illustration alone. So now I will use some actual examples to explain the differences. These are examples of fluoroscopy and CT images of chocolate-covered almonds, commonly sold at convenience stores in Japan, still sealed inside the packaging. The fluoroscopic image on the left is brighter, where X-rays pass more easily through areas that are thinner or have lower density, and are darker, where X-rays have more difficulty passing through areas that are thicker or have higher density. The enlargement of the fluoroscopic image shown in the upper center area shows a larger number of white spots inside the chocolate. Those are from air bubbles contained in the chocolate. In this way, fluoroscopy can be used to investigate what is inside an object of interest without damaging the object. On the other hand, it is difficult to observe the individual chocolates, which appear to overlap in the fluoroscopic image. It is also difficult to determine the detailed status of the bubbles. Therefore, CT is useful for obtaining a more detailed understanding of the bubble status. CT scans of the same object can produce either cross-sectional images like the one shown in the lower center, or three-dimensional images shown on the right, which can be used to observe each chocolate individually. Note, however, that the opposite areas appear black or white compared to the fluoroscopic images, with areas that X-rays pass through more easily appearing darker. CT also requires a longer time to acquire images than fluoroscopy, but CT provides a more detailed understanding of object structures because cross-sections can be viewed at any position and shapes can be viewed three-dimensionally. Therefore, it is important to use each technique appropriately, such as by using fluoroscopy for quick inspections and CT imaging for more detailed analysis. This is the system used to acquire the transmission and CT images shown in this presentation. It is an Inspectio SMX 225 CT FPD HR Plus microfocus X-ray CT system. The system offers three key features. The first is the large, high-resolution flat panel detector, which enables the acquisition of high-resolution images with a large field of view. The second is the high output and high contrast images enabled by an X-ray generator that generates a large amount of soft X-rays in combination with a detector that is highly sensitive to soft X-rays. The third key feature is the new fully automatic CT scanning function with the high-performance computing system that ensures almost anyone can easily perform high-speed CT scans. So far, I've given a broad overview of X-ray transmission and X-ray CT imaging and described the system used in the examples presented. Next, I will describe the first example of observing a joint between dissimilar materials. The observed sample consists of two different types of sheet metal welded as shown. The size of galvannealed and aluminum alloy sheets to be welded were both 100 millimeters long, 30 millimeters wide, and 1 millimeter thick. A 30 by 30 millimeter area of each sheet was overlapped, and then the joint tool, with an 8 millimeter diameter, was rotated as it was pressed into the hole from the aluminum alloy side to weld the joint with friction heat. Two types of samples were prepared, one with pressure applied for a long time, and the other with pressure applied for a short time during the press, insertion, and rotation. These are examples of cross-sectional and three-dimensional images obtained. Image magnification can be changed in CT parameter settings, but in these examples, cross-sectional images were restricted to the area around the joint. As I mentioned earlier, for cross-sectional and three-dimensional images, the lower the density or smaller the atomic number in area, the darker the image appears, whereas the higher the density or larger the atomic numbers in the area, the wider the image appears. The image on the upper left is a transverse cross-sectional image that shows the aluminum alloy near the edge of the joint. It visually shows, as a white ring, that the metal being coated was discharged as the sample softened due to the friction heat during tool rotation. Immediately to the right is a longitudinal cross-sectional image, where aluminum alloy deformation caused by pressing in the tool, internal defects in the aluminum alloy, gaps around the joint, and discharged metal can be observed. The same gaps and metal discharge were also confirmed by sectioning the sample using an EPMA system, which is consistent with the results from both instruments. In addition, elemental analysis using an EPMA system also confirmed that the discharged metal was zinc. Finally, the specialized image processing software was used to create the three-dimensional image shown on the lower left, which can be used to observe the joint three-dimensionally. As I mentioned in the earlier slide, elemental analysis of the same sample using an EPMA system showed that the discharged metal was zinc. The zinc was from the galvannealed steel sheet coating that softened and flowed out from the perimeter of the joint during welding. Because a higher joint strength can be expected for samples without any zinc remaining in the joint, it's important to observe the zinc discharge status from the joint samples. Next is a comparison of CT images from two different samples joined with different pressurization periods. The upper images are cross-sectional and 3D images of a sample with pressure applied for a short time. The lower images are cross-sectional and 3D images of a sample with pressure applied for a long time. Both samples discharged metal from the joint perimeter and developed gaps, but both the cross-sectional and 3D images immediately show apparent differences between the two types of samples. The longitudinal cross-section images from the two samples prepared with different pressurization conditions were used to measure the protrusion, indentation, gap thickness, and gap angle from the aluminum alloy at the joint. The results showed that the sample with short pressurization was thicker at the protrusion and indentation and had a smaller gap angle. Since the mechanical properties of the joint are said to be affected by dimensional differences at the joint dimensions can be quantitatively evaluated non-destructively by measuring dimensions in CT cross-sectional and 3D images. I will also show you an example of a similar friction stir-welded joint between two types of sheet metal, but with different dimensions and made of different materials. As confirmed in the observation results I previously introduced, in addition to observing the metal discharged as the sample surface coating softened due to friction heat, rippling was observed that was presumably caused by tool pressure, and a black crack line near the joint interface surface between the two metal sheets was also observed. Here's a summary of observation example 1. Using X-ray CT imaging to observe inside the samples of friction stir-welded galvannealed steel and aluminum alloy sheet materials enabled visualization of zinc coating discharged from the galvannealed steel sheet surface that can cause cracking. The example also confirmed that CT imaging results were consistent with EPMA results. In addition, the results showed that dimensional measurements in cross-sectional images can be used to quantitatively evaluate joint dimensions that affect mechanical properties. Because X-ray CT imaging is non-destructive, it can be used to observe three-dimensional structures over a large area when deciding whether to cut samples for detailed cross-sectional observation using an EPMA system. X-ray CT imaging can also be used to acquire information about internal structures in order to consider differences in mechanical properties before destructive testing by mechanical testing machines. Thus, it can be useful to use CT imaging in combination with other testing equipment. So far, I've talked about the first example of observing a joint between two dissimilar metals. Next, I will describe the second example of observing a joint between dissimilar metals. Observation samples were prepared by butting the edges of two different pieces of metal sheet, friction stir welding them together by applying the tool pressure from the aluminum alloy side, and then cutting the sample into strips, as shown. CT imaging focused on the area near the joint surface, with a portion of the image magnified in the same manner as in example 1. These are transmission and CT images of the sample. The transmission image shows the presence of small carbon steel fragments inside the aluminum alloy that occurred due to the friction stir welding. Furthermore, the cross-sectional video images obtained by CT imaging provides detailed confirmation of how the steel fragments are distributed. Finally, the three-dimensional video image makes it immediately apparent how the carbon steel fragments are distributed throughout the overall sample. This shows the results from comparing cross-sectional images from two samples prepared with identical materials and conditions. Despite no differences in the materials or conditions used, a void in the aluminum alloy is visible in only one of the two samples. By loading the cross-sectional images acquired by CT imaging into a specialized image processing software, volumes and other quantities can be analyzed. These are results from analyzing the relative volume of carbon steel in the two samples prepared with identical materials and conditions. It extracts the carbon steel fragments from the aluminum alloy and visually shows differences in their distribution and volume. These images show large volume fragments in red and small volume fragments in blue. The volume analysis results can be shown not only in cross-sectional and 3D image, but also as a histogram. The histogram indicates the void volume on the horizontal axis and the number of voids on the vertical axis. The volume ratio of carbon steel fragments versus aluminum alloy was also calculated. For the two samples in this example, the results did not indicate any major differences in the volume ratio with respect to the aluminum alloy or in the distribution of volumes. Similarly, by loading the cross-sectional images into specialized image processing software, the volume of voids can be analyzed as well. Those results show that the friction stir welding caused voids in the aluminum alloy in only one of the two samples, as mentioned earlier when discussing cross-sectional images. Volumes in these images are color-coded based off the same color scale as described earlier for carbon-steel fragment results. Thus, volume analysis results show that the volume of voids detected in sample 2 is about the same or less than volume of carbon-steel fragments, and the volume ratio of voids with respect to the aluminum alloy is about 0.3%, which means that the volume ratio of carbon-steel with respect to the aluminum alloy is about a factor of 10 less than the volume of carbon-steel. This is a summary of observation example 2. Carbon-steel fragments and voids were observed that occurred due to friction stir welding carbon-steel and aluminum alloy joint samples. Three-dimensional image data analysis software was used to analyze the fragments and voids to quantitatively determine their respective volumes and distributions. As indicated by the testing described above, X-ray CT imaging is clearly useful for observing or analyzing inclusions and defects distributed three-dimensionally throughout samples. Finally, I want to briefly summarize some key points from the overall presentation. The results showed that when evaluating joints between dissimilar metals, X-ray CT imaging can be used to visualize three-dimensional structures and analyze metal fragments and voids that occur due to welding, though different things can be evaluated depending on the material, size, and dimensions of the samples being observed. Furthermore, X-ray CT imaging can be used in combination with an EPMA system to observe detailed structures or determine constituent elements, with material testing machines to evaluate mechanical properties, or with other instruments to visualize internal structures without destroying samples. That means CT imaging can be used to evaluate the same samples as tested by other equipment. Testing samples with multiple instruments can also be useful for confirming the consistency and validity of respective test results. This completes my presentation on using X-ray CT imaging to non-destructively observe joints between dissimilar materials. Thank you for your attention.
Excellence in science. Shimadzu.